All right, everyone, I don't know if there's anyone at the back who'd like to join us. Please come and sit down if you want to watch our panel. Shall we kick off?
So I hope everyone enjoyed their lunch. And now we have a panel on lookups with Anna Rose from zkValidator, Mary Meller from the Ethereum Foundation, Andrija Novakovic from Geometry, and Ariel Gabizon from Zeta Function Technologies.
Fantastic. All right, so today we're going to be talking about lookups, lookup tables, lookup arguments. Actually, maybe we could start with this is actually a genuine question. Am I supposed to call it lookup tables or lookup arguments, and what is the difference?
The table is the table. The argument is the argument that you've looked something up correctly in the table.
So the argument is looking up something in the table?
Yes.
Okay, I guess that makes sense. As a topic, what is the preferred term?
I don't know.
All right, we'll leave it at that. Lookups is what we're going to go with. I want to do a short history of lookups, where they started. Maybe we can start with lookup, which I think lookups are an older concept, but yeah, maybe in this context, where does the story of lookups start?
Well, actually, as far as I know, it starts with a paper that Mary co-authored.
Co-authoring is the best I can give that. The idea was Suna Jacobson's, actually.
The idea?
Yeah.
Ah,
Okay.
cool.
So this is a paper called Aria. That's the first time
Yeah.
I've seen them. And then I think Lookup was maybe the protocol that started getting into the mainstream consciousness in some sense.
I hadn't realized that there was this earlier work. Can you actually talk a bit about that?
So this was a very, very early, I would say, zkVM project. zkVM project.
Okay.
The original.
Well, the original zkVM as well?
Not the original. There were ones before, but certainly an early one. And it was really looking at TinyRAM. So that was the VM that it was using. And it was sort of saying, if we have this zero knowledge proof, can we prove TinyRAM? And for that project, we were using this SNARK, which is like linear time. And because it's linear time, you can then have very nice properties about the theoretical proving time of the system. It's an early work, so I say theoretical, and I kind of mean theoretical. But at the same time, the idea of if we use lookup tables, this could make things a lot faster. Yeah, it came up. It was useful.
Was it written out in it or just suggested?
It was written in it.
Oh, cool. Nice. Okay, and then we have lookup.
And
it stopped traffic.
So this button doesn't change anything.
I think your mic's on.
What was the question?
And then there was lookup.
Then there was a lookup.
Yeah.
That I think popularized lookups in snarks. I guess then there was almost in parallel, but there was the Halo 2 lookup argument, which is a slightly simpler version of lookup, maybe, or like every time I look at lookup, I get a little confused.
The streets of Paris are also confused,
right.
it sounds like.
I don't know how much further to go.
Well,
so
let's keep going. So after those two works, I'm kind of curious, is there anything between that and Culk in terms of lookup work?
Not that I'm aware of.
So there's actually an interesting history, because I think a little, maybe in parallel or a little before, there was what's called the log derivative lookup that interestingly, people came up with independently. A few people, Liam Egan, Ulrich Habeck, that wrote it the most clearly. So his paper became the standard for that, and others came up with it independently. And in the end, it ended up being used in sort of this new generation of lookup protocols, starting from Culk.
Cool. Let's talk about Culk. Where does the idea for that start?
So the idea actually started from a membership argument. So typically when people are doing membership proofs, they would do it with a Merkle tree, right? You would have this big Merkle tree, and you would say, I know a path to this entry, therefore I belong in this set. And then you would prove all that inside a snark if you want to do it in zero knowledge, which means you then have to decompose all of your hash functions, and it sort of takes a little bit of prover work. And the thought here was that if we don't have too big a set, if we're not talking 2 to the 60, but more like 2 to the 20 or something like that, can we do better with pre-processing? To which the answer, KCG commitments are amazing, is very much yes. Yes, we can. We can do things where if you've done a pre-processing step, the actual amount of time it takes you to prove that you're in this set is logarithmic in the size of the set without going through this MP arithmetization process. And it was while working on this where we were there if we extend this, and if we're not just trying to prove one person in a set, but lots of things in a set, that kind of works too, right? We can make that work. And this is really what Calc was. It was the result of that. I mean, I made the association between this is a lookup table almost immediately, because I was very familiar with lookup at the time. So that helped.
Cool. And then I want to talk a little bit about the most recent work as well. I know that I know Calc is just sort of like a monumental one. And then there's semi-Calc, I think. There was another variation.
I think you should talk about semi-Calc.
Let's do it.
That's something. Does it work?
I think so.
No, that's something very different. That's what Mary said. That if Calc originated from one lookup argument, then semi-Calc was a step back. So it returned to have this very efficient one membership argument proofs. And we did a lot of customization and a lot of small sub-protocols to make this extremely efficient.
Cool. Why did you take that step back there?
So because we were mainly interested in can we kind of maybe modify Calc plus, which came after Calc, to allow that one membership proof. And to easily integrate it with current proving system like Plonk and stuff. So that was our thinking, how we can just easily plug it without too many changes.
When you say efficient, how efficient is it?
Oh yeah, so okay, the proving time, as we know, does not depend on the size of the set. So the main goal was that you always have this EVM trilemma, as our colleague Vei would say, that if you want to have snark-friendly hashes for Merkle trees, you pay a lot in the smart contract for updating the group. So our idea was okay, can we remove the Merkle tree so that we make everything cheap, verification, proving time to be constant, and that you pay a really cheap in amount of gas in the contract. And that's what it unlocked. So you don't need the trilemma anymore.
Cool. Okay, I want to talk about everyone's recent work on this topic too. Mary, what's your latest on lookups?
So our latest work, Ariel was also on this work, is probably Baloo. And this was a work that Arantxa was really taking the lead on, but it was saying, okay, we have Calc, we have this thing that's really nice in terms of how it depends on the size of the table. But actually, because we'd really been focusing around doing it in the case of just one lookup or a very small number of lookups, we had this additional cost, which was saying that the number of lookups you do, it's going to scale quadratically in that. And at the time we were there it'll be small, it'll be fine. And quadratic isn't great, if we're being honest, not if you're trying to use it in the same context as people would be using the Halo 2 lookup argument or the lookup argument. So it then became sort of the big question of, is there a way for us to get that prover time down? And this is really what we were focusing on, and we were able to get it down to not quasi-linear, but not far off. It's m log squared m, and that cost, the m log squared m, is coming from a trick to do with pre-processing all of the KCG commitments.
Cool. What's your latest? You have
well,
two works, right?
The latest on the lookup front is something called CQ.
Didn't you have a second part of that?
Well, so in CQ, and yeah, to a degree in all this sort of latest line of lookup works, starting from calc, we use this technique called cached quotients.
CQ.
So we have a paper where we use cached quotients not for lookups, but for fast linear operations. So that's a paper called CQ-Lin that Liam and I wrote.
Cool.
Yeah, but maybe to give just a little, also say a word about CQ, but give a little context. So yeah, so again, sort of the big question was, can you have a lookup argument where the prover time doesn't depend on the table size? And sort of calc was the breakthrough that answered yes, like essentially, yes, essentially. And the basic idea there was, okay, let's go down to the sort of a subtable of values that we're actually going to use and work just with that. And then sort of the breakthrough step is, how do you prove in time that doesn't depend on the table size that what you're working with is really a subtable of the original table and not some values that are not in the table at all. So then there was this sequence of works, calc plus, Lookup Baloo, that all sort of used this paradigm of, let's try to go down to a subtable and do that as efficiently as possible. And then, okay, when we're already in a small table, you can do whatever. And sort of what happened in this last work, CQ, is that's why I'm saying it's interesting that sort of the histories came together. There was this log derivative lookup that was not in this works of have the prover time depend on table size. It did depend on table size. But then sort of what happened in this work CQ is we said, okay, if we look at this log derivative lookup and we just try to run it in a way that the prover doesn't depend on table size, and we sort of leverage pairings for that, it can work. It basically works. So there's no need to go down to a subtable and work with it. We can sort of directly work with a log derivative lookup on the original table in prover time that doesn't depend on table size, at least when we have pairings. We can do that.
I want to ask you, we keep talking about these lookup tables and the lookup arguments using the lookup tables. Where are these stored? Because I think when you use the term table, you think sort of like an index, something that's, would need some sort of storage. I sort of know maybe the answer to this, but yeah, where does it exist in space? Is it in the math? Hidden in the math? Where is it?
I think the answer to this is like a little bit dependent on your use case. So when we're talking about calc, and when we're talking about CQ, and when we're talking about Baloo, we're very much talking about these pre-processed tables. And in this situation, you would assume that the prover knows the table, and the verifier has seen the table in the past, but they don't need to reread it because they've already seen it. They've already done their pre-processing. There's also a type of lookup table called a dynamic lookup table. And this would be something which only the prover ever sees because they're really creating the table during the proof.
But is it a separate file entity? Is it like, I'm still trying to get that tangibility of it.
Oh, so yeah, like as Mary said, once you read that table and you do some operation on it, you will just get like a bunch of elliptic curve points, so to say, and you just need to store them somewhere. And then depending on the case, you can have some service that will serve that. You can like store it in memory, in RAM, whatever.
Got it.
But yeah, I just like now. You can treat it just as a byte that you have the way to parse. And
cool.
use it later.
I have another question, which is about, and you sort of touched on this in the story of the trajectory of these different systems, but it's the composability with the other parts of systems. So like lookup tables, do they work with all other forms of folding schemes, like we heard about, or all other forms of, I don't know, IOP, polynomial, like, you know, is there, like, do you have to almost design these to fit specifically in a proving system to work together with some of these other techniques? Or can they be like almost generalized and work with all of them?
I think it goes pretty smoothly, especially if you look at the Protostar paper. So there they talk about just generic interactive protocols where the prover sends some messages, or we'll call them polynomials, verifier sends randomness, prover sends some messages, verifier sends more randomness. So this model that also it's what I call the RAP in an old blog post, randomized error with pre-processing. And then you check some low degree equation on the combination of the randomness and the prover polynomials. So yeah, so all our protocols, you know, copy constraints, Plonk gates, R1CS, lookup, all the lookup arguments we know, they sort of fit into this this framework. There's a little nuance with using pairings for the verification as you do in Calc and CQ, but the short answer is just the lookups are another equation that the verifier is checking. They're not that special. Like, it's not that hard to combine them.
Could you then switch out the lookups of Halo 2 and some of the newer work if you wanted to?
That's kind of discrete log based, so you need pairings to use in your work.
Okay. What's an example of a system that you could use it with?
Well, I mean, we are actually, Andrija and I and others, we are working on at least the version of, so CQ needs pairings. So at least the fork of Halo 2 that uses KZG, and we are working on adding, being able to use CQ instead of the Halo 2 lookup argument there. And we're excited to see like what the performance boost will be.
Cool. Do you want to say something about that too?
Yeah, so Ariel just asked me in Yingtong, do you want to do this? And we said yes. It was very simple conversation. And yeah, we kind of did it. We still didn't benchmark on this very important circuits that we want to optimize, but we have like a lot of plans to do on that trajectory. So yeah, hopefully we will release some stuff soon.
In an interview we did a few months ago, you talked about the sort of the additive homomorphism and the multiplicative homomorphism. Does that play any role in which systems it can work with?
Yeah, absolutely. You need this generation of protocols from Calc to CQ. They need KZG. They need a pairing. Yeah, they need some multiplicative thing.
Got it.
I suspect that might be fundamental as well, although I'm not sure.
Would you say, well, actually, can lookup tables be used with things like Starks?
Yes, but not the more recent line of work. So the stuff that relies on pairings, Starks, pairings, they're not, pairings are sort of something which is not something you can instantiate with hash functions, put it that way.
Okay.
But if you're thinking about some of the older schemes, certainly Lookup and Halo 2, yes, you could do that with Starks.
Oh, cool. One of the questions, when I was prepping for this, I asked a few people what they wanted me to ask, and I think everyone had the question, some variation of like, will there be a time where we don't need these? Like, are lookup tables an optimization because other parts are not fast enough? Or, yeah, is it something that will eventually be replaced?
I mean, it's always going to make your prover time faster, will we get to a point where we don't care about proof of time is really what you're asking, I think, there. To which, yeah, I'm not sure I'm the right person to be the judge of that. Hopefully.
I mean, I think right now there's some optimizations that are not competing with each other. This new line of lookup protocols, since it requires pairings, it is competing with the sort of Fry route. And yeah, I mean, it's hard to see it's interesting to see what will happen with that. Because yeah, using smaller fields, and even codes that are not even Fry, that are even faster than polynomials, that they're getting a lot of speed ups that you can't in the pairing KZG elliptic curve world. In the pairing KZG elliptic curve world, you have these tricks like in these new lookup protocols. It's hard to even now I would say the speed ups are sort of comparable. They come from you're gaining from different things, but it might be that right now the total speed up you get on both tracks is sort of comparable. I mean, I'm biased toward more the pairing side. Yeah, and in the pairing side, I think you'll always use tricks like, fast lookups using pairings. I mean, why not use it if it gives you a 5x or... yeah, and in that track of elliptic curves, you won't have this thing that the basic operations are so cheap that it just doesn't matter.
Cool. So how much time do we have? All right. I think it would be a good chance for us to open up the floor. I'm wondering if anyone here has any questions for our panelists about lookups, lookup arguments, lookup tables.
Thanks for the discussion. Andrija, perhaps a question for you, if you'd comment on what are the difficulties of incorporating these log derivative based lookups together with the existing Halo 2 system? That would be really interesting.
Oh, so yeah, it was just something new that didn't exist, and we had to, as Ariel said, the pairing is required, so it kind of break a lot of abstractions that we had. So we needed to modify every single piece of the Halo 2. And also these protocols, which are coming with very specific pairings, if I can say, very specific pairing equations, which are not batched KZG. We needed a smart way to automatically batch them, because what you see in papers is okay, you have all these pairings, and you can batch them. But when you get to something dynamic, you don't know how much lookups you will have in your circuit, or you want to keep that generic. We had to add more work to make it all generic, and yeah, we were able to do it. Thanks for the question.
A follow-up would be do you, after this experience, see any room for improvement in Halo 2, in the interface or the abstractions or anything like that?
So, okay, it didn't break abstraction. I think abstraction of how you write circuits and stuff is very nice. It was just abstracted from the commitment scheme, which we couldn't do anymore. So mainly that's why we had to break everything. But we still like Halo 2 a lot, yeah.
Thanks. I like it too.
I think there's a question here.
Thanks. So this is going to be a little crossover moment between our panels. Ariel, you said that there's sort of two tracks that are towards optimization, so the Fry track and the pairing track. But I'd wager there's also the folding track, where we now require curve cycles, and so we can't have efficient pairings on both sides. Do you see these things as incompatible, or is it just a temporary setback?
Well, actually, I really enjoyed the panel before, and the one thing I disagreed with during the whole was that you need curve cycles. I'm of the opinion that the number of scalar multiplications, during the fold, right? when the number of scalar multiplications is like 5, 10, 15, it's not that bad to do it without a cycle. And I mean, that's, for example, that's what Aztec did, right? They have this aggregation with like 15, 18 scalar multiplications. They just do it non-natively. So I think, so that's, I think empirically, yeah, people, maybe because of the eventual complexity, in any case, they don't go to cycles for a small number of, scalar multiplications.
One of the more recent creative uses of lookups that I've heard is looking up state transitions in a VM. What are the most common use cases for lookup arguments, and what are some of the biggest wins that we can get from lookup arguments?
I mean, one thing that sort of would be quite cool to be able to do, I'm not sure that we're totally there yet, but hopefully we will get there, is when it comes to trying to do range proofs in circuits at the moment, we're much better at it than we were before. It's getting faster. It's getting to the point where it's no longer, there's this terrible operation which is going to massively drag down the speed of your circuit. And one of the reasons for that is we do have these additional tools. We do have these lookup arguments. We do have these ways of arithmetizing things. If we can get to the point where we can just say to developers, when you're writing your circuits, do a range check on every single element to make sure that it's within the range of 64 bits, then we can kind of natively tackle 64-bit architectures, and that would be nice.
There's a question back there.
I have like a bit of a two-part question. So with some of these lookup argument architectures where you have constant time lookups, like as an analogy to suffix trees, like sure, you can search a substring and a string corpus in constant time, but you have the pre-processing cost of creating a suffix tree, and also your memory requirements are like an order of magnitude higher because you have to pre-process the string database as this tree-like architecture. And I guess my question is there like an increased cost borne by other parts of the system with these constant time lookups? And if not, can you kind of motivate with intuition why that's not the case?
You mean an increased cost in the pre-processing?
Or maybe the memory requirements, just basically like what's causing these lookups to be constant time in the input and not depend on the size of the table?
Yeah, so it relies heavily on pre-processing, and the pre-processing now is the new bound on the table size. So for a table of size n, you need to do a pre-processing of n log n group operations. So that sort of seems to cap the current table size at I don't know, 35 bits, something like that. I mean, hopefully we can actually get 35 bits and run the pre-processing. If you ask, like, what is the magic that allows you to not depend on the table size, it's this homomorphicity of operations like a pairing that sort of allows you, for example, to compare polynomials that you've never computed. It allows you to compare polynomials that you've only computed the commitments of, and sometimes computing the commitments of those polynomials is much cheaper than computing the polynomials themselves after you do a pre-processing.
Did you have a part two, or was that both of them? Good. I think actually, in terms of timing, I think we're right at time. Yeah, thank you all for this panel. Thank you for listening.
Thank you.
Okay.